Okay, welcome to Lecture 1 of a graduate course being taught at the University of Alberta in the winter of 2021 on single agent search. And this is an introductory lecture that is going to provide an overview of the types of things that will be covered in this course. And the plan is that this entire course will be placed on YouTube and be made available both for the students in the class and anybody else who's interested in learning about heuristic search. And so we want to start out and think about, well, what is a heuristic search problem and how do we solve them? What are we trying to do? So generally speaking, a heuristic search problem is a problem where we're trying to find a path, at least what we're going to be looking at in this class. And so you could imagine this idea that I have some sort of state that's a start state in the state space, and I'm looking for some sequence of actions that are going to get me to a goal state. Okay. And so I'm trying to find this sequence of actions, and the question is, the real question or the problem we're trying to solve is, what is the sequence of actions that is going to get me there from the start to the goal, or is going to transform the start to the goal state? And this can model quite a lot of different problems. And so one of the most common problems that is modeled with this is pathfinding. And so let me just show an example of that here. And this example here is a video from early development on the game Dragon Age Origins, which was released around 2010. And so this is just an early prototype. And one of the single agent search things that exists here is given a character in the game. We want to ask the question, how do we get that character pathfinding from a start location where we see the character there and a goal location? And here you can see a path being incrementally planned and refined in the world. And so this is one of the example problems that we've been looking at. But there are many other problems that would fall under the broad title of heuristic search that will be looked at within this class. And so later in the class, we'll talk about how something like this is actually done, and we'll go through that. But something that's really interesting is that the field of heuristic search, although it's more than 50 years old at this point, so for instance, the A-star algorithm came out in the late 60s, and we had original search algorithms coming out, something like Dijkstra search came out before then. We've seen in the last few years significant recent changes in what these algorithms are, such that maybe many of the things you might have learned in a textbook or that are currently in textbooks are missing significant updates in what we know and understand about these algorithms. So I just want to go over a couple of those things. So if I model this problem here, you see I modeled this as I have a start and a goal, and we're trying to find a path. And we usually think of that as sort of a forward search trying to find a path. So one thing that's really changed significantly is our understanding of bidirectional search. So I have a start and a goal, and it seems obvious that if I sort of search outward, that I'm going to get some large frontier of work, and that's going to be really expensive, as opposed to having a start and a goal, and maybe doing some sort of bidirectional search here, where we can split up the work in each direction, and we can and try and get savings there. And so this is an idea that's been around for 50 years, but it was actually only very recently that we understood the theory behind bidirectional search. And when we've understood the theory, it's really caused an explosion of new work in that field, an explosion of understanding what's going on. Many of the algorithms that were worked on before we had the theory had serious issues in the work that they were doing, because they were not theoretically based. And so one of the things we're going to cover in this class is bidirectional search, understanding of how we do it properly and what is the theory behind it. And so that's going to be something that's really changed. That'll be very interesting. Another thing we look at is we look at the quality of the paths that we find. So very oftentimes we look at an algorithm like A-star, and we might have heard that A-star is optimal. Now, it actually means several different things of what it means to be optimal. And so we're going to look in detail about what it actually means for A-star to be optimal. But there's also like very simple variants like weighted A-star. Okay, so weighted A star can find suboptimal solutions. When you teach A star, you almost always teach weighted A star because it's a one-line change to it, and it um, can find suboptimal solutions much faster than optimal solutions. And there's many common problems where suboptimality or small amounts of suboptimality don't really hurt that much. That is, we don't require optimality to be able to use a solution from a problem, and we may really need something much faster to be interactive or something like that. Okay, so weighted A star then is a very common algorithm, but there's actually many other algorithms that have been introduced, and so most people again don't know about these algorithms. Some common ones are things like explicit estimation search, dynamic potential search, and these algorithms have a bunch of trade-offs. So very recently, there's been some work that looks at basically variations of weighted A star that keep the strong properties of weighted A star so that they're very simple to implement, but have better performance and have some very nice properties about having to avoid node re-expansions and things like this. And so we'll be talking about some of these suboptimal algorithms, how they work, and have a better understanding of what is going on in suboptimal search, how it can be done, and how we can get better performance. Again, also, if you look at search, what you often see is that, like if you go look at a standard textbook, what you'd often get is you get A star and IDA star. And as we said a second ago, A star is optimal. And so we often say, well, you can't beat A star. Of course, there are many ways to do that, and many papers say, how to beat A star. So of course, one way that you could beat A star is by doing bidirectional search. But if we look at A star and IDA star, what we find out is they have really bad worst case performance. So if you were to be looking at A star, if A star has n expansions, then there's cases where A star could do 2 to the n expansions of n states. So you might think, I use A star and everything's going to be solved, but actually no, A star can be exponentially worse than some other algorithms. And there's some real problems there that come up, and so that's something that needs to be understood of where those problems come from and how we can fix those. So there's new algorithms for A star. And for IDA star, we often write IDA star's performance as B to the D, and that's something we'll get into in the next lecture. We'll be looking at where that comes from. But it ends up that IDA star's worst case performance is B to the 2D. Okay, and so that's significantly worse than B to the D. And there's a new algorithm, again, that does a much better job of dealing with this, which has performance, which is B to the D times C star, where C star is the log of C star, where C star is the optimal solution cost. And again, we'll get into some of the details of what's going on there. And so what's important is actually that there are some very interesting cases of problems we might want to solve. And when you just take very standard, very simple assumptions, then A star and IDA star do work well. But once you start to work on a richer set of problems and you go into richer spaces, then you're going to start seeing cases where we might hit some of this worst case performance, and we want to be able to avoid that. So we'll be looking at things like that. Some other things that we'll touch on in the class. Sorry. Okay, here we go. Sorry. Some other things that we'll be touching on in the class is one problem. We'll just spend a little bit of time on this, but it's a very interesting problem, is multi-agent pathfinding. Multi-agent pathfinding is the problem of solving multiple agents at one time. And this can be formulated as a single agent trying to get from the start to the goal. But there's also ways we can decompose this into separate algorithms. And there's just a ton of work that's exploded in the last few years on multi-agent pathfinding, because there's so many applications of this, particularly when we're looking at like autonomous vehicles and things like that, especially in controlled environments, or something like an Amazon warehouse can be modeled by multi-agent pathfinding. And so we'll be looking primarily at CBS, which is called constraint-based search, which is a new algorithm, it's about 5 years old now, 5 or 6 years old, but it's an algorithm that many of the new approaches are based on. And so we'll take a look at some of that work in multi-agent pathfinding. But there's a lot of work going on there. We're only going to be able to touch a little bit of that. And then I just want to point out, we'll spend a little bit of time looking at learning. So there's a lot of work that is people have looked at recently on trying to use learning for different parts of search. And we're just going to touch on some aspects of that. But learning in search is something that is maybe an open area right now where there's some interesting challenges there. And so we'll just take a look in different places where there might be opportunities for using some of the things that have gone on in machine learning and applying them in principled ways to search problems that we might be looking at. Okay, so these things give us a motivation of why heuristic search is something that we might be interested in, and why, sure, maybe A star and IDA star, but there's a lot of details behind that, a lot of new algorithms that have come out. And so that's a lot of what this class is going to be focused on, is understanding those new algorithms and understanding some of the pieces behind them that allow us to solve more complex problems or more interesting problems than we've been able to in the past. And then we'll be looking at some of the regular things that are behind here, like where do heuristics come from and how do we use them effectively, and the general principles of what our state spaces look like, and how we can take advantage of the properties of our state spaces when we're designing algorithms. Okay, so if we think now, we want to just be a little bit more explicit. So we've had here thinking about our state spaces. We're going to talk about formally what is a heuristic search problem. And to think about this, we're going to think about what is the input and the output. And so for the input, I need some representation of a state space. And there's several different representations. We'll talk about those. I'm going to need something on a start state that tells me where do I start. And I need something of a goal state. And the goal state may not be an explicit state. It might be a test to say, does this state meet the properties of a goal? That is, I may be many goal states, and implicitly I'm searching between them. And then the output here, the output is going to be a path from the start to a goal. Okay. Now, the thing to understand about this is that, we may have different requirements on the path. Sometimes we want an optimal path. Sometimes we want a suboptimal path. We may need to bound the resources that are being used when we find these paths, or other things like this. So let's look at some of these things in a little bit more detail. So what is a state space defined by? And there's two common definitions for a state space. And one of these would be, well, a state space just could be a graph, a graph made of some set of vertices and edges. And this is called an explicit representation. That is, I'm going to explicitly give you every state in the world. I explicitly give you the transitions between them, and you can reason about all of those. But we also could have an implicit definition, and particularly when our problems are large. So if we could imagine an infinite state space, or a state space that may be, just too large to ever be able to write down 10 to the 19th states in something like the Rubik's Cube, which we'll look at in a second, or there may be problems that are even larger than that. So the full state space is too large, but we may be able to solve a problem within a subset of that state space. So if I want an implicit definition, then what I'm going to do is, implicit, I need to define a couple different things. So we have a start state. And given a start state here, we can use a start state to generate an entire graph by using a successor function. Or if we don't have a successor function, we may just have a list of operators that could potentially be applied within the state space. So this is a way of taking a state and actually getting the neighbors of that state, that it's not explicitly represented, but I might be able to apply some operator to get those in the world. Okay, so implicitly, then that's going to give me the operators, or this is going to give me my neighbors. So these are functions that are applied. The other possibility is I could just have a successor function. So it may give me explicitly the neighbors that I can get, or my operators may be things that I apply. So we have to distinguish between those. But this would be like legal all of these would give us legal next states that I can transition to. And so those are both models that we could use of an implicit state space. And so if I'm, depending on the size of the problem and depending on whether, again, it's explicit or implicit, it's going to really change what are the methods that I can use for building heuristics or solving these problems. And we'll be looking at both of these and some of the trade-offs that come from both of those and the algorithms that we use differently in each of these different state spaces. Historically, most state spaces in AI have been implicit, but there's been a lot of recent work on explicit state spaces. And there's a slightly different community that's looked very particularly at road networks. So how do we do pathfinding with GPS or things like that on a road network? Okay, now our goal is to return a path. So a path is going to be a set of states. So what is a path? Path is going to be a set of states, S1, S2, S3, all the way to Sn, where S1 is equal to the start, Sn is equal to the goal, and then depending on whether we have an explicit or an implicit state space, we have different constraints here. So for instance, we might say that S from I to S of I plus 1 in a path has to be an element of the edges that are in the graph, if it's an explicit graph. Or we might say S of I plus 1 must be an element of the successors from the successor function of S of I. But basically, it's the idea that this path has to be connected as we're going along. And then the optimal path would be, the path of shortest length, or we might have a cost function, so be the lowest cost. And a suboptimal path, of course, would be anything beside that. Now, these are the basic input we need to solve just a search problem. So I've said search here, but I haven't said anything about heuristics. And so here we could have additional information. Okay, and so additional information we might have is we might have a heuristic. Now, heuristics mean very different things in different parts of literature. So in the scope of this class, a heuristic is meaning it's a numerical estimate. It's a numerical estimate of the distance, and it could be to the goal or to between any two states. And so here, if you were to be looking in other fields, you might find that they use heuristics. In fact, there's a lot of fields that use heuristics in their name. And those heuristics can mean very, very different things in different fields. So here, when we talk about heuristics, we're going to be talking about numerical estimates of the distance between states. And we'll look at properties like admissibility and consistency and things like that, and the impact that those have on a search problem. Something that is often around, but maybe you wouldn't necessarily find it defined explicitly in many problems, but is that we have constraints. And so constraints, if we think about heuristics, are numerical values that operate thinking between two states. Constraints are basically on guidance that are going to be whether we not generate or do not generate a successor. Okay, so I might have many successors, but I might have a constraint that says this is a successor you don't need to generate. And I have some reason why, or we're going to prove that we were able to do that. And so we will be looking at constraints sort of early in the class as part of our state space definitions fairly early on, but we're not going to formally handle constraints until a little bit later in the class. But as I said, constraints are something that are not necessarily stated explicitly all the time. I think they should be, because there are things that we can generate, and they do have a very broad impact on the performance that we actually get in practice. And so what we could do now is we could look at a bunch of states, and we could think about, is it explicit or implicit? Is the goal explicit or implicit? We could think about what is a state, what is an operator, what might the cost function be? And so we'll look at a couple of these. The first problem we might mind to look is the problem of pathfinding. So pathfinding is going to be example domains. So let's go here into our next page. So and let's talk about this. So we want to know, is it explicit and or implicit? And then is the goal explicit? And then we can think about what is a state. I won't necessarily write this down, but we'll just use this. What is an operator? And what is a cost function? Okay. So we're going to think about these as for a couple different state spaces. So we could think about pathfinding. And let's think pathfinding on a graph. So this on a graph here could be a graph it could be represented in many different ways. It could be something like a grid. So a grid actually implicitly represents a graph and is very easy to extract out. So we wouldn't necessarily want to write it down as an adjacency list or some other graph format, but we get it implicitly out of a graph and maybe whether states are blocked or unblocked. Okay, so think about pathfinding on a graph. We get asked this question. Is pathfinding on a graph explicit? Well, is the state space explicit? You always can pause the video here and try and answer these questions to see if you understand it. And what we'd say is, yeah, okay, so pathfinding on a graph is often explicit. The state space is given to us explicitly. The goal, we may be given an explicit target. In the most basic problem there are more advanced versions of problems that may have a less explicit goal. Like I may want to get within 1 meter of a target. And so that would be a implicit goal, but in the most basic definition, we're going to have an explicit goal. A state space is just going to be x, y coordinates. An operator is going to be a direction, and the cost is going to be actually the distance traversed. And so this, for instance, could be 1. If we're on a 4-connected grid, this would be something like 1 or the square root of 2. And sometimes people might use 1 or 1.5 just because that's easier to represent. And so let's go here. If we go back and look at these videos that we had, what we're going to see here is we can look. So this is, as I said, the pathfinding or an early video from Dragon Age Origins. Dragon Age used a grid representation at the lowest level. And so the characters here, all the pieces of these paths are on a grid for doing the pathfinding problem, but there's other problems like smoothing that they use the grid for occupancy information, but the grid is, you're not required to always travel from grid center to grid center, so we can get smoother looking paths. Okay, and just to show some of the other pieces here, this is looking at a very high level of a pathfinding request. So this is really, really zoomed out, looking at a pathfinding request that goes all the way across this map. And there's a character somewhere down there, you can't really see it, that is doing the walking to walk along that path. Game isn't designed to be zoomed out that far, but you can see how maybe global pathfinding requests were possible within that game. We might have things like obstacles. So in this case, we have these traps that are on these squares. And so the character here, there's a trap there. So here we can have different costs than just straight distance requests. I'm going to walk around that trap, but if I disarm it and I go back, then I should be able to walk over that trap. So we can have dynamic costs in the world, again, depending on exactly the problem that we want to work on. So this is often the case that we might look at very abstract models that when we get to the real world, we have to change those models to get them to work in practice or to get them to be able to solve the more interesting problems that work there in practice. This is just a picture going back to the previous map of a high-level abstraction of what is done to build a graph, which is an abstraction of the original grid that exists at the lower level. And as I said in one of the later lectures in the class, that we'll be looking at how this is done in practice. And this is something that's very, very effective in games because of the speed that we need for pathfinding and because some of the properties of the state space. Okay, so let's go back and so just go back to what we're writing here. If we look at, so this is on a graph and thinking about a very general definition here. So this is something more like a grid graph or something like that. We could now think about a road network. Okay, so a road network is going to be very similar to this. It's going to be very explicit. The goal is explicit. A state space is now going to be, it's now going to be an XY coordinate. Oftentimes those would be integer up here. And now we have an X and Y coordinate that may be actually a graph node. Okay. And now my operators are going to be edges. So this is definitely, thinking about direction here, that's definitely on a grid graph. So I'll just put that there. On a grid graph here, we have edges. So we're going to be sort of moving arbitrarily where these edges are going to represent roads in the world. And the cost here could be the length of an edge, but it also could be something like travel time. So these are two possibilities. And what you use here makes a big impact, whether you're thinking about just the length, the distance traveled, or the travel time, because a freeway, of course, you travel much more quickly than traveling on city streets. Okay, so I'm not going to show, I guess I can show one example here. So this is an example of the road network of Colorado. And this has very, very different properties than you see, for instance, in games. Here, the dark region sort of in the middle right, a little, actually I can point to it here. I guess my mouse doesn't show up. But the dark region, sort of a little bit above the middle, is the city of Denver in Colorado. And then you can see, you can actually pretty clearly see a highway heading out to the right, a highway heading out to the left. And there's a lot of really, really short roads that are sort of locally going outside of the major cities. And so there's a lot of work. We're not going to talk too much about it, but there's a lot of work that's been done on explicitly taking advantage of the properties of these sort of road networks. Okay. Now we could start to think about combinatorial puzzles. And so one of the really common puzzles that we're going to use, and really this is just an example of many different state spaces, but it's very easy to talk about. And so this is one actually we'll use very broadly, is something like the sliding tile puzzle. And the sliding tile puzzle has a very interesting history to it. The Rubik's Cube was something that was really popular when I was a child. In the 80s, then that was something that everybody was trying to solve, the Rubik's Cube. In fact, I have some Rubik's Cubes here. We'll talk about these. So this is a 3x3 Rubik's Cube. And we also have something like this, which is a 2x2 Rubik's Cube. And there's some very interesting properties about the 2x2 versus the 3x3. The sliding tile puzzle is something that in the 1890s was very popular. So this is a much older puzzle. But people were trying to solve this and didn't understand necessarily the mathematics of that state space. And so just to, again, look at what the sliding tile puzzle looks like, it's something like this, and a sequence of operations here. This would be an example sequence of operations that solves the sliding tile puzzle. And so here, well, we'll get to, once we solve it, we can see what the goal is, but we're trying to get these states all sorted. And we'll be able to do that effectively here. Okay, so that was the optimal solution for the sliding tile puzzle. And now let's go back and look at this. So the sliding tile puzzle, is the state space going to be explicit? So we potentially could, something like the 4x4 puzzle, we might be able to do it explicitly. The number of states is going to be generally so in this case, there's 16 tiles. So you think about the first tile could be in 16 locations, the next could be in 15 locations. And so the size here is 16 factorial. There's a symmetry, so it's divided by 2. And if you look at this, this is sort of just at the range of what you might be able to represent. It was a number of years ago that someone actually, Rich Korf, was able to do an explicit breadth first search through the sliding tile puzzle, the 15 puzzle here. But generally speaking, we're not going to try and store that directly. And for any bigger puzzle, then that's not going to work. So is it explicit? Generally speaking, we're going to say it's not going to be an explicit state space. Now, is the goal explicit? Yes. So there's a single goal state we're trying to reach, and we know exactly what that goal state is. What is a state? Well, the state is going to be all tiles and their locations. And there's a lot of different ways we can represent that. Later on in this class, we'll be looking at those representations. The operators are going to be up, down, left, or right. And oftentimes here you might think about, well, I could move a tile in these directions, but for the sliding tile puzzle, it's actually easier to think about moving the blank up, down, left, or right. And the cost here is unit cost, usually for all the tiles. Although we will be looking at variance. For instance, maybe the tile costs different weights depending on the number that's on it. So you could imagine that I'm moving things around in a warehouse or something like that. Some things are heavier, some things are lighter, and so then I have to pay a different cost for that. So this could be modeling something like a warehouse where you're moving objects, although then you might have more empty spaces in between. Okay, so that's the sliding tile puzzle. It's a very common combinatorial puzzle. And another combinatorial puzzle that's very common that we'll be talking about at different points in the class is the Rubik's Cube. So as I was showing you a second ago, the Rubik's Cube is a 3x3 puzzle, and the Rubik's Cube was made popular, was invented by Erno Rubik. Again, it was popular in the 1980s, and there's a number of different results that have been shown for that. So if we look at the Rubik's Cube, the Rubik's Cube has about 3 times 10 to the 19th states, so it's not going to be stored explicitly, but the goal will be explicit, generally speaking. Now, we can look here, and I can show the video of solving. This is one of the common test instances used, and this is an optimal solution to solve this. And this is very different than the type of optimal solutions, or not optimal, but the type of solutions that humans tend to use when they're working on the Rubik's Cube. But this is what an optimal solution does look like. But for instance, if you were trying to build better macros for your solving this, where you have macros like moving pieces around locally, then you might be looking at, well, I want the best move that swaps these two pieces and these other. So we may want to swap like 2 pieces on the top layer and leave everything else intact. And then we might look for a macro that does that. And then it would be an implicit goal, because some of the cubes would be allowed to be in indeterminate states after we applied a set of operators. Okay, so the state is going to be all cubes, their locations, and orientations. The operators then are going to be the turning of the rotate a face. And the most common operators here would be that we rotate 90 degrees or 180 degrees or counterclockwise 90 degrees. So there's generally 3 operators times 6 faces would be 18 actions that you would have. And the cost for this typically is unit cost. But there's very interesting things you could do here. So if you were modeling something like a speed solver, where you might take into account the orientation of your hand, and you might use that to say, oh, well, if my hand is this orientation, then I can move this face much more easily than if it was than some other face. And so you might take into account something like that when measuring how long it would take a human to actually execute a set of operations. Oh, sorry, I wasn't showing this here, so I was writing this down. So it's not explicit. The goal is explicit. We're thinking about cubes, locations, orientations. We're rotating a face, and we have unit cost. Okay. So Rubik's Cube is really common, and there's lots of other puzzles that we could go through here and try and look at. So like rush hour is a common one. There's things like edit distance. So let me just show this. I'm not going to write it down on this screen, but edit distance is, for instance, something like, how do I get between the word 4 and 5 by changing 1 letter at a time and always having a valid word at each step of that process. And so if you want to try and see if you can do that, you should pause the video right now, because I'm about to show the answer. But here's the answer. So 4, foul, foil, fail, fall, fill, file, and 5. So we see 1 letter changed each time. And if we were to take the entire state space by looking at all English words that are connected together, we could try to do something like plot them in a 3-dimensional space. And if we do that, you can see a little animation here that shows what that state space looks like. Okay, and so here, just going back, so something like edit distance. Sorry. Now this could be implicit or explicit. Depends on whether I want to think about my dictionary be sitting around or not. So it could be both. but it's generally small enough that we could do it explicitly. And is the goal explicit? Oftentimes, well, I'm going to give you a word and another word to get to, so that would be explicit. The state is just going to be a word we're currently in. The operator is change a letter. And the cost is always going to be unit cost, going from one to the other. So there's other problems. Again, if we think about having a multiple DNA between different creatures in the world, like a mouse versus human DNA, we might want to compare the DNA or RNA or look at a protein and say, how close are they to each other? So we could look at this problem. We have some sequences here, and we're asking, how close are two sequences to each other? What's the path that is closest? If we try to line them up and say, like maybe do they match here? Do they mismatch? Is there a blank? There's different cost functions that you can use, and those can be used for measuring differences. And so this is equivalent to finding an optimal path through an n-dimensional hypercube. So that's just another example state space. And just to show one more here, another state space. So topspin is another common problem. Towers of Hanoi. In Towers of Hanoi, we're trying to move disks around. Towers of Hanoi is interesting because the length of a solution is exponential. And so many of our problems do not have exponential length solutions, and that changes the types of things you'd want to do for solving something like that. So here's another one that I wanted to go at, and let's go back and look at this. So I have a robotic arm, and let's just look at some animations on this arm. So here I think about, like, I'm trying to move the tip of the arm. This is showing a simple search, trying to get the tip of the arm to a given location, which is a little tiny green square. It may not be visible there, and here's an optimal solution that looks at that. Robotic arm is very interesting because we have a workspace and a configuration space. So here, what we're going to do is we're going to draw some obstacles, and obstacles in the workspace look very different than in the configuration space. And if we move the arm around here, so we're moving it here in the workspace, we see that it moves around in the configuration space. And then if we're trying to get a path through the space, then we can see that search of the arm corresponds to actually search in the configuration space. We're not going to spend a lot of time talking about robotics. There's some very interesting work, quite a broad amount of interesting work that's been done. One of the researchers that does a lot of work here in robotics is Max Likachev at Carnegie Mellon. But we'll look at how we define these problems. And robotics is something that is sort of akin to, well, so if we look at road networks, there's sort of a whole sub-community that's focused on the specific properties of road networks. There's a similar community that's looked at robotics, and it's quite a broad range of techniques that have been used in robotics. And again, this isn't a robotics class, so there is a lot of overlap in many of these ideas, and we'll only be able to touch on those very briefly. So going back to our different pieces here, when we think about a robotic arm. So is the state space explicit? For something like here, where I have like two joints in the arm and no other degrees of freedom, then it could be explicit, but typically these are not explicit, because once I get more joints or more degrees of freedom, then this gets really expensive. Is the goal explicit? So almost everything we've looked at so far doesn't have an explicit goal, or does have an explicit goal, but robotic arm doesn't. Now, because typically the goal is defined within the workspace, that is, I want to get the arm to some location so that I can manipulate an object, but where all the other joints of the arm are when I'm able to do that manipulation aren't necessarily specified. So it's just that the tip has to be specified, but not everything else. So the state would be the arm configuration. An operator would be movement, so it'd be movement of a joint. And the cost is could be many different things. We might sort of say unit cost for operations, but it might be much more complex depending on the low-level dynamics of the motors that are running the arm and things like that. So this could be very dynamic. Okay. So the other thing is that there is, I look at these are all sort of one example of one state space. There is a general area of research called planning. And in planning, there's a factored state space representation. That is, we don't just think of the state space as a state space that we apply operators, but we think of a state as a bunch of variables and the values that they have. You can explicitly reason about the operators that exist on variables and values. In fact, operators are usually described in terms of constraints on the state space. If the variables have these values, then you're able to apply this operator. And then in these sorts of state spaces, you can automatically build heuristics or build constraints that allow you to solve problems. And so I'm not going to be talking about planning, but this is a very rich area of research that currently uses many heuristic search techniques. So the last thing I'm going to do to finish off this lecture is I'm just going to show some sample algorithms. And one thing I'm going to say, maybe I should have said this a little bit earlier, but if you've made it this far, is that this course is going to have two things that we're going to look at a lot. And so we have, over the years, I've spent a lot of time building demos, and these demos allow us to play with the state spaces and videos as well. And so if you go to my webpage, and I'll give a link to that, there should be a link at the bottom of this video, but I'll give a link to that as well in a minute. There are animations of many videos, and there are animations of many different algorithms. And so we'll be able to use those, and I'll be providing a link from many lectures. Almost every lecture, there'll be a link to a demo that demonstrates some aspect of that. In these lectures here, I'm not going to be covering what goes on in those demos in great detail, but there will be a video, or a demo tie-in to almost every lecture. So if we're looking at algorithms here, we can look at things like A star and watch how A star performs. And so we can see here on a simple map that if we run A star, we've expanded almost all of the state space. We could look at something like weighted A star that is going to be focused more on, on states that are close to the goal. This is a really hard problem though. So once it gets sort of around this, this wall and around to the other side of the wall, then it does much less work than A star would, but there's still a lot of work that could be done there. We're going to look at building heuristics. So here's an example of where the same problem where I have a very strong heuristic or much stronger heuristic, and so it's going to allow us to solve this problem. All the other videos so far have been sped up because the search is too slow, but this one we didn't have to speed up. So we're going to think about how we can build stronger heuristics. And so there's many other videos and demos that are available and that will be available corresponding with each of the lectures. And so just to wrap up here, let me say that these demos are at movingai.com. And so you can find them there in the menus. There's a subdirectory here, single agent search, that has the demos for single agent search. And so these should all be connected together in the future. So the last thing I just want to say is to think about, if you've taken, for instance, a graph search class or an introductory to graph search, you may have learned a bunch of algorithms there and might say, well, why can't we just apply those algorithms and use them? And so there are a number of different reasons for that. And again, it's going to depend on the problem that we're working at. So if we're looking at a problem that has an explicit graph, and then on something like a road network or things like that, then it may be that we can use those algorithms directly, but it may be that we want to think about how we can use smart reasoning to do much better. And that's sort of the AI aspect of it. Like, what sort of knowledge can we combine? How can we combine knowledge and search to make it more efficient? And so there are some fundamental differences between graph theory and AI. So one thing here is generally we're going to ignore our data structures. When we think about the complexity of our algorithms in this class, we're going to think about node expansions. So we're going to think about operations that we do on states, but so make that just a little bit clear there. So operations on states, we're not going to be thinking about, well, what are the data structures? I will from time to time mention data structures that can be used, but there's often very specialized data structures because we're making specialized assumptions. And so we're not going to think about explicitly in much of our runtime analysis how it depends on the data structures that we use. But the other thing here that's very different is we have memory constraints. So we're very often going to be solving problems that are going to be much larger than what is able to fit into memory. And so when we, think about that, then like we're going to have to do very different things than you could do in an explicit graph. And one of the particular things here we have to worry about is duplicates. And duplicates are going to come up repeatedly in the course, and so we'll talk about that at the times that they come up. Another thing we're going to be thinking about very often is we're thinking about a branching factor that is constant. And of course, this isn't true in practice, but we're going to sort of model things as every state I can make a constant number of operators or constant number of actions that I can take. And so that's going to change the types of algorithms that I can do and the complexity. So very often in a graph problem, this would be called a sparse graph. And I don't worry about like that the number of neighbors could be equivalent to the number of states in the state space. And so that's something that's going to change the types of algorithms that we want to apply. And so generally speaking, if something is polynomial in the size of the state space in graph theory, then that seems to be great. But if we have exponential problems or too much memory, then polynomial time is oftentimes going to be too expensive. So polynomial space in the graph is too expensive. Okay, again, that's going to depend on the problems that we solve. We'll see some problems where that's the case, some problem where it's not. And so we have to just be aware of those differences. And again, it depends on the types of problems that you're trying to solve. And the field of search in AI has really split to consider exponential and polynomial domains, which is something that wasn't always explicitly considered in the past. And so this wraps up the first lecture, and we'll have another lecture that follows up on this and starts to look at how do we model our problems, how do we model the search trees, and how do we get into our basic search algorithms. We'll very quickly move out of these basic search algorithms into some of the more advanced things that I talked about in the introduction to this lecture. So I hope to see you coming along with this lecture as it's posted, and we will continue shortly.